Welcome again. We continue. Our next speaker is Mondher Chouikhi from Université De Gabès. He will talk about cubic oscillator, geometric approach, and zeros of Eigenfunctions.
Thank you.
Thank you very much.
Thank you. Welcome. So before I get started, so I would thank the organizing committee and all the staff of IMPA for their hospitality and giving me the opportunity to be here. So my talk will be about cubic oscillator, and I like the title. Oh no, sorry. Donc, we will go in the opposite direction of what Jorge had said in the morning, from geometric to analytic. And in the end, we'll return to some geometric result. Okay, so the talk will be about a second-order differential equation with polynomial potential, which is an example of differential equation with irregular singularity at infinity. So we will use the complex, we will recall some basic of complex WKB based on Fedoruk's work, Mikhail Fedoruk. Fedoruk, his method. And we will announce our main result in the in this point and in this point. Okay, we will go on. So some basic of the ordinary differential equation in the complex plane with polynomial potential. We have this result by many authors, Shibuya and Hill, Teichmar, Olver. We can find everywhere. So in either Stokes sector, defined by this way, the non-trivial solution to this differential equation are of two types. Dominant solution, which increase exponentially along any ray in the sector, and subdominant solution, which decrease exponentially along any ray in the Stokes sector given by this equation. And general fact about the zero of non-trivial solution. Non-trivial solution, because the trivial solution is the solution equal to zero. It is a trivial solution. So, general fact about the zero of solution, there are sample, so they're accumulating near a translated anti-Stokes ray on this form and at infinity. And the distance between the kf 0 and this translated anti-Stokes ray is of this form. We use Neval linear theory to prove this result. Prove it in. And when the degree of the polynomial is odd, solution are of odd order. And a general fact about the non-trivial solution, if the polynomial is of degree m, so the order of the solution are entire in the complex plane, and the order of solution are m plus 2 over 2. So, in the odd degree case, we have always infinitely number of solution of 0, and quasi-exact solvability may appear in the case when m even, like the degree 4 or the degree 6 polynomial. This is general fact of this type of classical regime equation defined by this ordinary differential equation. So, this is an example of Stokes ray in the case of cubic. In the blue are the Stokes ray, and in the red, dashed red, are the anti-Stokes ray. So, at infinity, the zero will accumulate near a translated ray of this red ray. And this is what we give. So outside a disk in infinity outside a disk of radius r, we have the 0 are accumulated in the translate critical array in this way. So this general, so Shibuya has considered this eigenvalue problem, which is Y is subdominant in two disjoint Stokes sector, and as we had seen that the Stokes sector divide the plane equally in this form. So Shibuya has established this result that the set of eigenvalue are is a discrete set, the geometric multiplicity of every eigenvalue is 1, and we have this asymptotic of eigenvalue in infinity. And we will call this eigenvalue problem as the classical eigenvalue problem studied by Shibuya and many authors. So we can find all this result in the book of Shibuya and Hill, and the asymptotic of the 0 near the translatory critical array is in this paper, and in work of Stephen Bank and Gundenser. So Stephen Bank, also his first mentioned the first example, because Einhard Hill claimed that the 0 are near the anti-Stokes line, but Bank has, using Strode's theory, construct an example of a non-trivial solution, ordinary differential equation with polynomial coefficient with non-trivial solution that have 0 near, not the, near the anti-Stokes lane, but translated anti-Stokes lane. So the first who had constructed an example is Stephen Bank, and later Gunderson and the author in this paper. Okay, so going on, we will consider now this equation with a parameter lambda, which may be complex parameter. So this equation is well known, related to quantum mechanics, scattering theory, and so on. So the direct problem is for a given polynomial to describe the set of all non-vanishing lambda for which this equation has a non-trivial solution which is subdominant into Stokes region in C. What we will define later what mean by Stokes region and not Stokes sector. Stokes region. And what about the 0 of this eigenfunction, and what about the subdominance property in lambda and z? This is what Fedoruk had considered in the problem before. So this equation was studied by this author, and it is well known in the literature of, from the mathematical and physical point of view. So Fedoruk considered this eigenvalue problem when P is a real entire function. That means that we'll fix the real plane, the real PR R, real entire function, with boundary condition in plus and minus infinity. And Fedoruk has creating a universal algorithm to describe the solution to this problem. What Fedoruk has done is the topological, this algorithm is in 3 steps, topological level or 3 level, to find the topology of Stokes complex related to this equation, and the analytic level or the analytic step to find asymptotic behavior of elementary fundamental system, and finally the algebraic level to describe the global solution, the global, and to describe the group of monodromy O related to this equation. So from one fundamental system to another, we have a transition matrix to describe the link between this fundamental system. Okay. In the second point, Fedoruk gave a description of the condition determining the accumulation rate of the spectrum. When we have the spectrum is a sequence lambda n, so does this sequence accumulate near a given array? So for this problem, Federico give an answer and describe the condition of determining accumulation rate of the spectrum, and the description of asymptotic density of eigenvalue along such accumulation rate. So, inspired by Federico's work, we treat this inverse problem. So, for a given lambda, can we describe the set of polynomial p of degree greater to 2 such that the equation has non-trivial subdominant solution in at least 2 distinct Stokes regions. As had said, we will define what means by Stokes region. So if this set is not empty, can we describe the condition such that the argument of lambda is an accumulation array of the spectrum? And what about the zero of solution? Okay. We treat the case of cubic potential with 3 distant zero, and in all the rest of the talk, we will consider always PA is this our potential, and D is the set of all theta and A, because using an affine or a linear transformation, any cubic polynomial with 3 distant points has this form under a linear transformation. Okay, so going on, so we will start with the topological problem. We will describe all the Stokes region associated to this differential equation, and these results are contained in the talk of my colleague Loray. So we have the turning point, the zero of the polynomial, and we have this function related to the potential, and the Stokes line are defined by this equation, which are the vertical trajectory of the quadratic differential lambda square PA dz square. And the Stokes graph is the union of all Stokes line, and C minus the closure of the Stokes graph will give the Stokes region. And the Stokes region in the case of polynomial potential are of 2 types: band domain and half plane domain. Okay. And in the case of cubic potential, we have 5 half plane and at most 2 strip domain, and which are simply connected. This map, donc, so this map S maps invariantly each half plane to this form and each band domain to this form. Okay, this is an example of a Stokes graph. We have the 5 half plane. Here another example, and here another example. So this is an example of 4 polynomials, but as we had seen here, for the cubic, the difference between here, the 3, so is the relation between the turning point. In this case, the turning points are not linked. In this case, we have a link between 2 turning points, and in this case, so the 3 turning points are linked. So this is an example of 4-degree polynomials, and in the monomorphic case, the situation is more complicated. We may have spiral, we have circular domain, we may have dense domain, as Fawzi has told in his talk. So is very complicated, more complicated. So, okay, this is a quick comparison of what we have in the terminology of quadratic differential and the terminology in the complex WKB method. So the critical point are the turning point, infinite critical point and the singular point, and the horizontal critical trajectory onto Stokes line, vertical critical trajectory are Stokes line, and go on. We have all this terminology. So, we note here that, for example, for the first pole, if our quadratic differential have a simple pole, the simple pole for ordinary differential equation is like a turning point. So, in order to solve the first step of the inverse spectral problem, we must classify the Stokes graph. So the answer is from Glia's talk, and this, we use this level set, as Glia has said. So the level set, for example, for P over 4, we have this form, and we have this classification under some equivalence of relation of equivalence. These are the 4 types of graph. So this is a graph of type A. This is a graph of type B, of type BB, and of 3Ks. All these things are basically in our paper here, and we can find the method of Fedoruk in his book and in his paper. So we define what going on to the analytic problem, which consists to construct a local fundamental system of solution. So we define what is, by the way, so if we see here, so what this classification tell us? So in the classical case, as we had seen, so the information, we get information outside a large disk, and we don't know what happened in the interior of the disk. We go to infinity in 5 direction outside this disk, and we have some information here. He translated the critical ray here. But what happened here? We will see that what happened here will depend on what happened here. Is a kind of, before going to here, to infinity, to irregular singularity, maybe we should focus on what happened between the turning point. Because if we will see if the turning point will meet, this will give some result. If the turning point will not meet, there are some other result. The result differ between from one meeting to one meeting. Not every meeting. Not all the meetings are similar. Okay. So going on. So we define what is canonical domain. A canonical domain in the z-plane is a domain where this function S, the real part, is always monotonic, and for epsilon positive, to build the uniform criterion of the fundamental system in lambda in Z. So always we have in any point of this canonical domain, we have an assigned a path, a canonical path going to infinity with this condition, real S in plus infinity and real S in minus infinity respectively. So in this figure, for example, we have #0, #1 is canonical, #0, #4, for example, is canonical, #1 union B0, #2 is canonical, but for example, #0, #3 is not canonical, because if we fix a branch of S, we will have the union of #0 and #4 to pass to #3. We will go here or in the opposite direction, and real S will change the monotonicity. So this is not a canonical domain. So we have this theorem which mentioned the local fundamental system, and the important things here is which is a result well known in the result, and we have this duality of asymptotic, which is true as Z goes to infinity in the path, plus minus path, for lambda fixed, or which is true when lambda goes to infinity uniformly for Z in the epsilon. So going on, we define what is a elementary fundamental system to build the transition matrix is defined by this condition, and we have our group of monodromy. So defined as I had said, if we have two fundamental systems, it is 2 by 2 matrices defined by this relation. And Fedoruk had classified this matrices to 4 type. But in our work, we work with 3 type of transition matrices because we work we want a result of the first order. That means just bounded by this term in lambda. So if we need the other terms, we should use the 4th type of transition matrices. So the matrices are of this form. The first type to pass from one canonical domain to another canonical domain. By the way, this triply DLZ is called the Stokes data. Is the giving of a canonical domain and a Stokes line and a turning point. And this is the second type of transition matrices, and this is the third type of transition matrix. So, in order to build the maximal domain of applicability of WKB before going to the global problem, so we introduce the definition. We say that two half-plane hash k, hash I and hash k are admissible if for every 2 points in the two half-plane we have an admissible path that go from xi to xk. And for example, a Stokes complex that capture both of the half-plane we will call this complex joins to this we will call. So if we say that delta complex Stokes sector joins hash and hash if it capture both and so for example, two adjacent half-plane are admissible, and more generally, two half-plane are admissible if and only if there exists a canonical domain containing both. And the relation of admissible is reflexive symmetric, but not transitive, as had mentioned some example. And in a Stokes graph of type A, for example, there is no Stokes complex that joins any two distant half-plane with disjoint boundary. While in a tree case, we have any two different half-plane are joined by Stokes complex as given in the picture, in the figure. So we go on. So we will say that a direction theta is a cumulation direction to the ordinary differential equation if there exists a pair of disjoint half-plane such that this equation admits a subdominant solution, non-trivial always, in these two half-plane. The first main result is if we get K is a subset, a compact subset of C minus. By the way, this set is introduced as in the level set. Okay, here with short trajectory. So going on. We are here. So if under this condition we have no accumulation direction, and under this condition, if the Stokes graph is to P or a tree graph, we have an accumulation direction. And in the tree graph or Boutro graph in the nomination of, for example, Bertola and Mausero, we have this condition to have accumulation direction. So the idea of the proof is to cover the sphere with canonical domain and express each passage from one canonical domain to another canonical domain to get this classification. So this is the path going from, for example, upon z plus to infinity. So, and this is another path, for example. And for example, this solution will be subdominant here in H2, and the maximal domain of applicability of complex WKB will be all this uncolored domain. The same things with a solution that is subdominant in H1. The maximal domain of applicability of WKB will be all this white region. So we have this, established this result. And this is the number of accumulation condition for each Stokes graph. So for the zero, we had set this, we introduced this set of the zero of, if we take f is an eigenfunction associated to lambda n. Our goal is the description of this set as a in phi theta. So it is well known that is entire of and is of half is of order 5 by 2 and has infinitely many zero. So when A is described as above in this set is not empty and reduced to was when A is in the set and the Stokes graph is of type B and or if in 3 cases with this condition. Okay? No. So no. Okay. So the set is not empty, and we had a kind of dynamic here. So if the word is true, if we fix, for example, if I take, so I will mention the result, and you will return to this behavior quickly. So the result is this is the maximal domain of applicability in this case is the uniform dual aspect of WKB will be true in this domain P epsilon with this branch cut, and a tubular with white epsilon here. So we have this result, and the set had two components, an unbounded component will be in exactly, because it was claimed that the zero are in the tubular and not, maybe not in the short trajectory, but we prove that the zero are exactly in the short trajectory. So this set had two components, a bounded component in the short finite Stokes line and unbounded one in the infinite Stokes line. And for large n, which will depend on A, the the set will contain exactly n0 in L, which is analogous to the classical Sturm-Liouville problem. So if we treat the 3 cases, we have, if the solution is subdominant in H1 and H3, the zero of our eigenfunction will be here and here. And if the solution is subdominant here and here in H2, the zero will be here and here. This is the bounded one, the component, and this is the unbounded component. And in the 3 cases, for example, here, if the solution is subdominant in H4 and H1, the set of zero will be connected. In this form, the zero will be here and here. So our result proves that the location of zero depends only on the Stokes geometry. And our result gives a proof to a conjecture proposed by this author in the case of Sturm-Liouville equation with PT symmetry. PT symmetry, this means that we have this condition of similar result also was established by this author in this case, in this particular case. And our result confirmed this result in the case of d equal to 3. And not in the particular case PT symmetric. We have more generality in our result. And if we focus on the finite number of 0, the bounded set of Z, the set of 0, a conjecture on the interlacing of 0 was introducing by Mondher, so in this reference, and we pretend that our result will help to prove this conjecture. That means I will just explain before going on. So I will return to the set of, it is very important. Where is, this is the set. If we focus on the green, just on the green, the Stokes graph will be, this is -1, and this is 1. We have this, our Stokes graph, it's like this. This is A in the green. We have something like this. Okay, so as A, if we choose any point here, another A, so, and we will go to this point, a critic, this point. This point, sorry, we have this point is the intersection between all the red, the blue, and the green. Okay, so for arbitrary A in the green, this is the A position. We have this structure. So going on to A critic, in this sense, what we have is something like that. Every passage we have the Stokes. This configuration will be fixed, and the finite Stokes time will make something like here. And such as A go on to A critic, we will have sort of, and when A is equal to A critic, in this point, we have the three case. And this is very, very important in our work, and for the proof of some conjecture related to the location of the 0. So, going on. Okay, sorry. So, we finish. So, okay. Just I will mention some future direction. So, I go.
I think that we are already.
Okay.
So sorry.
So sorry. Okay.
I'm so sorry.
So this is some reference for the work, and we have a submitted paper on this topic. And thank you, and joyeux anniversaire, Frank.